In our previous lesson, we learned about quicksort algorithm. Now in this lesson, we will analyze quicksort. We will first look at some properties of quicksort, and then we will go ahead and try to analyze its time and space complexity. So we will try to see how efficient it is in terms of running time and space or memory requirement. Okay, so let's get started. The properties of quicksort that I want to talk about are, first of all, quicksort, just like merge sort, is a divide and conquer algorithm. Divide and conquer is an algorithm design paradigm in which we break a problem into sub-problems, and then from solutions to the sub-problems we construct the solution to actual problem. Okay, next property of quicksort is that it's a recursive algorithm. In programming, as we know, recursion is a function calling itself. Recursion is a natural choice in divide and conquer strategy. A divide and conquer algorithm is mostly implemented using recursion. Moving on, next property is that quicksort is not a stable sorting algorithm. We have discussed what a stable sorting algorithm is in our previous lessons. In a stable sorting algorithm, the relative order of records with equal key is preserved. When we learn a sorting algorithm, we sort a list of integers, but a sorting algorithm can be used to sort a list of any data type. In case of a complex data type, we sort on some property of records, on some key. For example, let's say we want to sort a list of points in Cartesian plane. Each record in the list here is a pair of integers. First integer is x coordinate and second integer is y coordinate. And let's say we want to sort in increasing order of x coordinate. We have two records here with equal x coordinate. If we will use a stable sorting algorithm, then 0.45, which is before 0.43 in the original list, will be before 43 in sorted arrangement also. But this is not guaranteed if we will use an unstable sorting algorithm. In the second arrangement that I'm showing here, elements are sorted in increasing order of x coordinate, but 43 is coming before 45. Partitioning logic in quicksort algorithm does not ensure stability. Okay, let's now talk about time complexity of quicksort. Time complexity of quicksort is big O of n log n in best or average case, and it's big O of n square in worst case. But the worst case can almost always be avoided by using what we call randomized version of quicksort. Let's now see how quicksort is big O of n log n in best or average case and big O of n square in worst case. This is pseudocode for quicksort function that we had written earlier. Let's try to calculate the running time. The first statement here is this if condition. It's a simple statement. The cost of executing this statement will be some constant. Let's say the cost of executing this is C1. If we will go inside the if condition, then we have this call to partition function. Now this is not a simple statement. We first need to figure out what will be the running time of partition function. This is the partition function that we had written in our previous lesson. If you can see, there are some simple statements here that will take constant time. These four statements are simple statements. Together they will take some constant time. Apart from these statements, we have one for loop. The statements inside the for loop once again are simple statements and will together take some constant time. Let's say these statements inside the for loop will take some constant time A, and these statements 1, 2, 3 and 4, let's say, will cost us B. So time taken will be an plus p. Let's say this constant a is also taking care of this statement where we are incrementing I for the loop. This particular line will actually, this particular statement, the for loop will run one extra time actually. But we ignore such small costs while calculating running time because we are interested in calculating the rate of growth for very high values of n. Okay, so the time expression here is an plus p, where a and b are constants, or in other words, this is big O of n. Remember, n here is the length of subarray that we are partitioning. Okay, coming back to our quicksort function. The partition function here is going to cost us big O of n. We can say that the cost for executing this statement will be some constant times n, plus we can add some constant here, but it will not matter because for very high values of n, the added constant term will be negligible compared to this a into n term. We have an assignment here to this variable p index. That once again will be some constant time. So in all, let's say we are taking b dash constant time. So overall cost of executing this statement is a into n plus b dash. And now we have two recursive calls. Let's see what will be the cost of these two recursive calls. In partition function, we choose an element as pivot. In our partition function, we are always choosing the last element in the segment of the array passed to quicksort, or the element at end index as pivot. I'm drawing an array of integers here, and let's say the whole array is passed to the quicksort function. So start is 0 and end is 7. 4 will be picked as pivot, and we will rearrange the array such that all the elements lesser than the pivot will lie towards its left, and all the elements greater than the pivot will lie towards its right. And now after the partition, we can make two recursive calls, one for the segment of the array to the left of pivot and another for the segment of array to the right of pivot. In this recursive approach, a balanced partitioning will be best case for us. In balanced partitioning, both subarrays towards the left of pivot and towards the right of pivot will have length equal to or almost equal to n by 2, where n is the number of elements in original array. So if time taken for this quicksort function is, let's say, tn, then both these quicksort calls in best case partitioning will take time tn by 2 each. So tn in all will be 2tn by 2, plus we will add an plus b dash and c1. Remember, this is the best case scenario for us. When we are saying best case, what we mean is all the partitions in all the recursive calls will be balanced. All the partitions will break a segment into two subsegments of equal length. Here in this recurrence relation, tn equal to tn by 2 plus an plus b dash plus c1, these two constant terms b dash and c1 will be negligible compared to an for very high values of n. And when we analyze time complexity, we always look at running time for very high values of n. So we can safely ignore b dash and c1, and instead of a, I will write c for constant because c looks good when I'm saying constant. So time taken in the best case is equal to 2tn by 2 plus c into n if n is greater than 1. For n equal 1, we will not go inside this if condition. Only cost will be execution of this if statement. So I'm saying that for n equal 1, my cost is c1. So t1 is c1. This recurrence relation that we are getting here for time is the same that we had got for merge sort. We can solve this recurrence and express tn in terms of t1, which is known to us. Tn is 2tn by 2 plus cn. We can write tn by 2 as 2tn by 4 c into n by 2, and we will have cn outside. This overall will be 4tn by 4 plus 2cn. And now we can write tn by 4 in terms of tn by 8 like this. This will be 8tn by 8 plus 3cn. In terms of some generic k, we can reduce this expression like 2 to the power k t n upon 2 to the power k. This will happen if we will go reducing k steps. In fourth step, after this step, when k will be equal to 4, this will be 16 tn upon 16 plus 4cn. I'm saying this is the first step, this is the second step, this is the third step, and this is the kth step. This is kth reduction. Now we know t1 and we want to express Tn in terms of T1. So in that case, n upon 2 to the power k will be equal to 1. If we will solve this, then k will be equal to log n to the base 2. So here Tn can be written as 2 to the power log n to the base 2 into T1 plus c into n into log n to the base 2. 2 to the power log n to the base 2 will be equal to 1. T1 is c1. 2 to the power log n to the base 2 will be n. T1 is c1, and this will be c into n into log n to the base 2, and if base is understood, then I can write this as log n. So this is what I'm getting. This expression is big O of n log n. nc1 is lower order term here. For very high values of n, it will be negligible compared to c n log n. For very high values of n, the rate of growth of time taken will be very close to c n log n for some constant c. So we can say that time complexity will be big O of n log n. Actually, it would be better to say theta of n log n. If you're not getting any of this, then we have a whole series on time complexity analysis. You can find a link to it in the description of this video. Theta notation is actually better metric. Anyway, in best case, we are big O of n log n or theta of n log n. Now let's try to analyze the worst case. Worst case for us will be when we will have totally unbalanced partitioning. Like for this array, which is already sorted, if we will pick the last element as pivot, after partition we will have only one segment. There will be no right segment. One of the recursive calls for left subarray will cost us tn minus 1 if we are saying that tn is the cost for whole array, and the other recursive call will simply return. Control will not go inside the if condition, so there will be some constant cost for the second recursive call. If we will have unbalanced partitioning in all cases, in all recursive calls, then the recurrence relation to solve is this: tn equal tn minus 1 plus c into n, where c is a constant. I'm ignoring other constants that would add up. They will be negligible compared to this term c into n for higher values of n. Of course, we also have a base case t1, which will be equal to c1. This tn is for all n greater than 1. This recurrence relation is really simple to solve. We can go on reducing. Tn minus 1 can be written in terms of Tn minus 2. So it will be Tn minus 2 plus c into n minus 1 plus, of course, we will have Cn here. So this will be Tn minus 2 plus 2Cn minus c. And we can go on reducing. Tn minus 2 can be written as Tn minus 3 plus c into n minus 2 plus we will have these terms 2Cn minus c. So now this is Tn minus 3 plus 3Cn minus 3c. If I'll reduce this further, this will be Tn minus 4 plus 4Cn minus 6c. In terms of some k, if we will go reducing k steps, then this will be Tn minus k plus kcn minus 1 plus 2 plus 3 plus all the way till k minus 1 into c. This part 1 plus 2 plus 3 till k minus 1 will be k into k minus 1 by 2. This is a simple arithmetic progression. So this is what we are getting. Now if I want to write Tn in terms of T1 that I know, then in that case n minus k will be equal to 1, and that will imply k will be equal to n. This expression will now be T1 plus k is now n, so this will be Cn square minus n into n minus 1 upon 2 into c. So my Tn finally is T1 is constant c1 plus, I can write rest of the part as Cn. I'm going to take this out. Inside it will be n minus 1 upon 2 and this part will reduce to n plus 1 upon 2. Overall, this is what I'm getting. I'm getting a quadratic expression of the form an square plus bn plus c, where a, b and c are some constants. A here is c by 2, a and b here are c by 2, and c is c1. This time expression is definitely big O of n square. To write in terms of big O notation, we will drop the lower order terms and the constants. Big O of n square is really bad, but as I had said earlier, worst case in quicksort can be avoided. In the partition function that I have written here, I am always choosing the last element in the segment as pivot. With this strategy, if my array is already sorted, I am always getting unbalanced partitioning. What we can do is we can have a strategy in which we can choose pivot randomly. So during this whole recursive process, we will not have a rule that only the end element should be picked up as pivot. Any element randomly should be picked up as pivot. What I'm going to do is I'm going to write a function named randomized partition that once again is taking the array and the start and end as argument. Now in this function, I'm first going to pick a pivot index between start and end included, by making a call to a function named random. This function will give me an index between start and end picked up randomly. Almost all the language libraries would have a random number generator function. Now the element at this pivot index is my pivot. I'll first swap this element at pivot index with last element in the segment, and then I can go with rest of the logic that I have in the partition function. So I'll simply make a call to partition function in the left that I've written here. In my quicksort function now, instead of calling partition directly, I'll call randomized partition. Now with this strategy, probability of hitting worst case is almost 0. Coming back to quicksort function, instead of calling partition here, we are going to call randomized partition. I'm short of space here, so I'll write it like this. This is randomized partition function. It's always wise to call randomized partition. Now let's try to analyze the average case. Once again, our base case T1 is C1. Now what will be my Tn? In average case, we will say that we can have all kind of split with equal probability. Let's say our array is split such that pivot lies at index I. The time taken for the left half in this case will be Ti minus 1, because there will be I minus 1 elements in left half, and there will be n minus I elements in right half. This I can be any index between start and end with equal probability. So I'm going to say that Tn will be average of all possible partitions or all possible values of I. Apart from this average cost, the cost of partition is some constant times n. So we have this recurrence relation to solve. I'm writing it down here. We are taking an average of all possible partitions here by summing up time taken in all possible splits and then dividing by n, dividing the sum by n. I'm not going to solve this one. You can check the description of this video for a link that has all the maths. This will also evaluate, this will also reduce to an expression that will be big O of n log n. With randomized partition, we can get average case running time of quicksort with very high probability. And this makes quicksort really cool, because unlike merge sort, its space complexity is very less. Let's now discuss space complexity of quicksort. Space complexity, as we know, is the measure of rate of growth of extra space needed. Extra space means space or memory apart from the memory used to store the original array, the original list. So space complexity is measure of rate of growth of extra space with input. I'm not going to derive this one for quicksort. You can check the description of this video for a link to a lesson where we have described how we can derive space complexity in case of recursion. The space complexity of quicksort in average case is big O of log n. In worst case, it's big O of n, but as we saw, worst case can always be avoided. Now log n is such small rate of growth that we can say that it's almost negligible extra space requirement. We can say that quicksort is in place sorting algorithm and in-place sorting algorithms should take constant extra memory. Extra space requirement must not grow with input, but log n for all practical values of n is very small, so we discount quicksort here. Okay, I'll stop here now. In coming lessons we will see some more sorting algorithms. This is it for this lesson. Thanks for watching.